Walk aboard a standard chemical product tanker, and you are standing on a hull designed to hold liquid weight at ambient pressure. Step onto a purpose-built gas carrier, and the entire architectural logic of the vessel changes. This gauge illustrates the exact legal and physical divide. Under the IMO IGC Code, the moment a liquid's vapor pressure crosses 2.8 bar absolute at a reference temperature of 37.8 degrees Celsius, it is officially classified as a gas cargo. That single metric renders standard tanker rules and structures obsolete. A standard hull cannot safely contain the pressure buildup of these cargoes on a hot day in the tropics. Operating on the gas side of that line requires mastering 5 interlocking pillars: thermodynamics, containment, mechanics, commercial liability, and STCW regulation. You cannot adjust one without instantly stressing the other 4. Advancing to the level of principal engineer requires abandoning the mindset of managing isolated pipes and valves. Mastery requires tracing an unbroken causal chain from the laws of physics directly to the ship's commercial contracts. Treating a gas carrier like a traditional pressurized system means ignoring the thermal laws driving that 2.8 bar threshold, an error that makes catastrophic operational failure a mathematical certainty. The foundational operational rule of a gas carrier is that you do not control pressure directly. You control temperature, and pressure follows automatically. This saturation curve maps the exact mathematical relationship for a sealed gas cargo. Every point on this line is a valid liquid-vapor equilibrium state. Raise the temperature, and the vapor pressure rises with it. But every curve ends at a critical temperature. For methane, that barrier sits at -82.6 degrees Celsius. Above that point, the substance is physically incapable of existing as a liquid, regardless of applied pressure. That specific physical limit is why the industry cannot engineer a pressure vessel strong enough to carry natural gas at ambient temperatures. Methane's critical temperature mandates deep cryogenic refrigeration. Thermal physics keeps the cargo contained, but chemical reactivity dictates the survival of the ship's hardware. Hazardous gases actively attack incompatible materials inside the system. Ammonia, for example, aggressively destroys copper alloys. Introduce a brass fitting by mistake, and you build a slow leak into the system. Even worse, if trace carbon dioxide contaminates the ammonia vapor, often through impure inert gas, the two react to form solid ammonium carbamate crystals. Those crystals physically choke pressure relief valves shut. Chlorine presents a different chemistry entirely. It demands absolute zero moisture control, or it forms highly corrosive acids that eat standard steel. Vinyl chloride monomer introduces yet another failure mode. It relies entirely on chemical inhibitors to prevent uncontrolled heat-generating chain reactions. Molecular physics and chemical reactivity cannot be negotiated with. They act as absolute dictators, forcing every subsequent containment engineering decision made by the naval architects. Looking at this aerial view of a purpose-built LPG carrier, you see how the industry translates extreme thermodynamic files into safe floating architecture. Independent Type C tanks are built to pressure vessel design codes. These thick-walled cylinders have massive structural safety margins and are rated for design pressures up to 18 bar gauge. Because that structural margin is so immense, the IGC Code dictates that Type C tanks require 0 secondary backup containment. Type A and membrane tanks go the opposite direction. They utilize low-pressure, thin-wall designs optimized for extreme cryogenic storage, operating near atmospheric pressure. Classical fracture mechanics cannot definitively rule out crack propagation in these thin primary walls. Because a catastrophic breach remains a mathematical possibility, a full secondary backup barrier is mandatory. This backup system must independently hold the cryogenic liquid for at least 15 days, maintaining full structural integrity even if the vessel takes on a static lurch of 30 degrees. The 15-day rule provides the precise window of time needed to divert the vessel to a specialized repair port during a catastrophic primary breach. Safely holding the cargo is only half the equation. Pumping cryogenic and highly volatile liquids out of those tanks creates severe mechanical vulnerabilities. Deep well and submerged cargo pumps sit at the bottom of the tanks, and they rely entirely on the cargo itself for their survival. The cryogenic liquid flows directly through the pump's bearings, acting as the only source of lubrication and cooling. This creates the absolute no dry run rule. Running one of these pumps empty instantly removes its cooling medium. Without that thermal protection, friction causes immediate mechanical self-destruction. This diagram of a shell and tube vaporizer shows exactly how thermal exchange dictates mechanical survival. We use seawater to warm extreme cryogenic cargo like LNG. The heat transfers across the tube walls, drastically dropping the seawater's temperature. If the operator allows the seawater flow rate to drop too low, the cryogenic cargo pulls too much heat. The seawater freezes solid inside the tubes, expanding and physically rupturing the heat exchanger. Mechanical failures on a gas carrier are rarely random manufacturing defects. They are the direct consequence of failing to protect the machinery's thermodynamic equilibrium. The moment a frozen vaporizer ruptures or a dry pump destroys its bearings, the physical failure instantly triggers massive commercial liabilities. A mechanical casualty at sea means the vessel can no longer fulfill the commercial obligations of its charter party. Every hour of mechanical downtime forces the ship to exceed its strict laytime allowances. That delay immediately triggers demurrage claims, penalizing the owner financially for the crew's operational failure. Under Hague-Visby rules, the carrier has a legal obligation to exercise due diligence to make the ship seaworthy. Loading chemically incompatible cargo or operating with damaged hardware is a direct breach of that legal duty. To prevent these commercial and mechanical disasters, the International Maritime Organization established a strict global competency framework to act as the ultimate failsafe. The original 1978 STCW rules were flawed because they measured time served, not actual skill. The 1995 amendments replaced that with demonstrable, competency-based assessment. You have to prove you can perform the task under pressure. That assessment draws a hard line between ranks. STCW Level 1 certification only authorizes you to perform tasks under supervision. Level 2 grants you independent operational responsibility over the cargo. Commercial contracts and STCW audits function as the final legal layers enforcing the physical and chemical laws of the cargo upon the crew. Ecosystem as a single, indivisible organism. A decision made in the cargo control room instantly affects the commercial contract and the physical survival of the metal. We can reverse engineer any failure path. A single molecular property forces a specific hardware requirement. Mismanaging that hardware creates mechanical risk, which imposes massive commercial liability, ultimately triggering an STCW audited competency failure. Port State Control inspectors know this chain. They actively board vessels to verify your operational competency, checking your ability to manage the plant completely independently of whatever paperwork your flag state issued. Your STCW certification proves you are legally qualified, but it is entirely generic. Ship familiarization proves you know exactly how the thermodynamic reality of this specific vessel is wired. They must align perfectly before you take the watch. True competency at the principal engineer level is the ability to simultaneously visualize, anticipate, and manage this entire physical and regulatory matrix, ensuring there is never a single point of failure.